be microfluidic channel or a nanofluidic channel. You separate all the blood cells out, other big abundant interference out, and let in desired a mixture of proteins that you want to analyze. Then you separate them, you focus them, and you detect them. And there are many, at least Robin analyzed about 90 or more different proteins and their elevated levels, and she discovered that there are about 4 or 5 of them that are strongly correlated with the late onset of neonatal sepsis. So then the idea is that can we actually measure the concentrations of these 4 or 5 different proteins, what we call biomarkers, and be able to accurately diagnose neonatal sepsis, and therefore we do properly treat these infants. So then if they're not coming down with an infection, then we don't necessarily have to expose them to antibiotics unnecessarily.
Fantastic.
Yeah, so that's something that we're working on.
So the tools to separate out the blood cells already exist and are in common uses, but this tool is specific to separating out these proteins.
No, we're building a device that would also simultaneously I shouldn't say simultaneously. Before we separate them and concentrate them, there is another section where we push out all the blood cells and other highly abundant interference. Yeah.
And just out of curiosity, because this is really very abstract thinking, especially at the nanoscale, what does it physically actually, what does the biologist get in the lab? Is this a little piece of silicon?
It'll be a cartridge.
Okay.
And right now the device that we're building is actually made out of a polymethyl methacrylate, fancy way of saying hard plastics. We're low cost, because silicon and its fabrication can be costly, so we're trying to achieve the same objective but using very low cost materials.
Sure, and
so
it doesn't have to go in the body, so it doesn't have to.
And so ideally, there are many groups all over the country trying to achieve this similar objective, where you have a handheld device and you have a cartridge and you take a very small blood volume sample, and the device will read levels of all these different proteins, and voila, you have an outcome. And doctor can, or clinicians can look at the data and say, okay, he or she can tell you your potential infection or disease and whatnot.
Great.
Yeah. So actually, last year I had a company based on the intellectual property that my group and in collaboration with a few other groups generated, and that company was actually able to successfully raise 1.4 million euros.
Yeah.
But eventually the company was closed because we couldn't raise further funding. But it was an interesting journey.
Does that have to go through lots of clinical tests and things
Eventually,
like that?
yes. Medical devices require FDA approval, and that can be a very costly and lengthy process. And
especially we're talking about a very specific population.
Well, last year's effort was actually on biomarkers for heart diseases. So biomarkers such as troponin, cardiac troponin I, and whatnot. And these are the biomarkers or proteins that are produced from your heart muscles when it's distressed.
Cool.
Okay, so maybe I should really. So these shows some different technological applications where germanium-based material systems can be used for night vision. And we had worked on, for many years, growing high-quality germanium on silicon, and that engineered substrate can be used to grow integrate other 3-5 compound semiconductors, and so maybe I should spend a minute to explain this. This is a cross-sectional view, schematic view of multi-junction solar cells, and they are typically used on satellites, space applications. What you see on rooftops, they're silicon-based, and these photovoltaic devices will not last very long out in the space because of the space radiation. When I say space radiation, includes protons, high energy electrons, gamma rays, and they destroy silicon-based solar cells in a very short amount of time. And so these are 3-5 compound semiconductors that can withstand space radiation. Not only that, we're stacking these different cells on top of each other. So imagine having batteries and stacking them up in series. So these cells actually are today probably the most efficient solar cells, about 43% or above. But they're expensive. And just to give you an idea, based on, I think it was a tutorial that I read that came out of NREL. So roughly to estimate about a square foot block with the focused sunlight can produce enough electricity to power your entire house, typical average house.
I want
how
one.
efficient, that's how efficient the solar panel is.
Only several $1 million.
I don't think they're that expensive, but it's a lot more expensive than silicon-based photovoltaic devices.
And is the expense the production or the materials?
Material cost.
Oh, okay.
Yeah, and so the way it works is that the top layer absorbs, as the color indicates, UV to blue to purple, blue region, and then the middle cell absorbs green to yellow, and then red to infrared, and so then you're grabbing different parts of the sunlight spectrum, and therefore harnessing energy from the broadband source, right? And each one grabs a small slice of that spectrum and turning that into useful energy.
Are you getting this, or do you have a question about what you want some clarity on something?
No, I'm
okay.
kind of baffled.
Yeah, it's great, huh? It's really so interesting.
So in the case of silicon, you're just grabbing very small slice of that, so it's not as efficient. But silicon is a lot cheaper than this. And certainly for terrestrial applications, that is household applications or earth applications, I think silicon devices, probably silicon photovoltaic cells, are probably one of the best ones to use because it's low cost. Yeah.
But the concept of the full spectrum, can that be integrated into silicon based cells? Is that what you're working on?
No, actually, our effort was to replace the germanium substrate with engineered substrates, because germanium wafers constitute roughly about half of the material cost of building this. And so if we can replace that with a high quality thin layer germanium on a very low cost silicon substrate, then we can potentially reduce the material cost. It turns out that also germanium is mechanically more fragile than silicon. Then if you can have a very stable, not as fragile substrate, it was a win-win situation. And also low weight. So these things have to go into the space, payload. And it was very advantageous. But today, certainly this hasn't caught on, but the field has moved on to a different technique to actually grow a very thin layer of these stacks on compliant substrates, even plastic substrates. So the field has moved on. Mm-hmm. Yeah. So here, finally, the project that Olga, Gunny, Christos, Nick, myself, you, and I believe, is that the person? He left, right?
I think that he was there the last. Wasn't
so
he there the last meeting?
So who was the one who left? Mathematician who was the original team member, but he left.
Oh, I don't remember.
Yeah. Okay.
Where does this image come from? That's a really great image.
That, I think, image is grabbed, more than likely, a nab from some. I don't know, actually. It was what Gunny grabbed it from. Someplace.
We'll need to reproduce an image that's cool that we have.
So
rights to.
I think this was the original diagram generated by Gunny or Olga, where it shows that a stack of different material systems or films to harness different energy sources that are available in urban settings: radio frequency, heat energy, infrared, number of different things. And so and in our case, what we're trying to do is, can we develop a material system that can effectively harness any sort of infrared signal that's out there? So that's what we're trying to do. And this is another project, so
Okay.
maybe I'll not
So
delve
can
into
you
it.
can you tell us, just going back to that,
Yeah.
and in relation to the previous example where you said the field has moved on,
Yeah.
what are then some of the problems that you need to solve to approach the idea of gathering infrared energy on these solar panels? So you had talked about the solving the problem of the expense, for example, of this multispectrum by having a very thin layer of germanium. But then you said
Oh, so what they do is now they grow these similar three stacks on a gallium arsenide substrate with a sacrificial layer on top. And so once you grow these stacks, then you etch out the sacrificial layer. While you're putting the plastic substrate on top, you just peel it off, and that becomes a solar cell.
and so is that the technique that you're now testing?
Yeah. Well,
Okay.
we're actually. So I've been working with the Air Force, in part with MCOR and whatnot. We've been working together to. So maybe I should rewind a little bit. So as I said, the field has moved on. Now these things are grown on gallium arsenide substrates, and then they flipped over on a very low-cost plastic carrying substrates, and that's the production line solar cells that you can actually purchase today. Now, my group in particular now is working on how we can make the metal lines, metal contacts that are formed on these solar cells stronger. And so maybe I'm digressing a little bit. So as I said, we work on a number of different things, and what we are lately working on is so it shows a picture of a satellite, and this is the website where I grabbed it from. And what we are doing is, if you can embed, okay, maybe I should give out a better analogy. So, have you ever seen concrete kitchen countertops?
Mm-hmm.
Okay.
Yeah, I love them.
So when they do, a lot of the new houses, when they do remodeling and whatnot, they put in these polymer plastic needles into the concrete, and it makes the concrete that much stronger.
Like fiberglass.
Yeah, fiberglass. Same principle. If you have metal lines, and if you embed carbon nanotubes into the metal line, metal film, then the metal becomes much stronger mechanically, and to a certain extent actually can show higher electrical conductivity. So imagine a solar panel that's out there in space, orbiting around the Earth, depending on the time of the day, or when it faces the sun, not facing the sun, the temperature fluctuation can be huge. So when the temperature fluctuation can be an order of several hundred degrees, things expand and contract to a large extent. And when you have materials that are stacked up with a different thermal expansion coefficients, they contract and expand and contract at a different rate, things can crack. And that's exactly what happens. These solar panels actually do crack over time and lose power generation. And so then if you can actually keep them connected electrically by having strong metal lines, then potentially can ensure the longevity of these solar panels.
So much of your work seems to me as a visual person,
Yeah.
have this a lot of symmetry and organization visually. But then when I look at this image here, it seems very random, like fiberglass.
Yes.
Is a formal organization of these nanotubes something that could increase the strength? Or?
That is a very good question. We like to find that out. So last week I got in touch with one of my colleagues, Randy Shunk, who is both UNM and Sandia employee, and he does terrific computational modeling to extract macroscopic material properties based on microscopic and nanoscopic structures. And so what we are trying to do is whether, to start with, let's say we embed these long needles, but very flexible in a way, into the metal matrix, and simply looking at their electrical and mechanical properties as a function of loading, how much you put in first, but they're randomly distributed. Then we can also think about other extremes where you have a metal film, metal layer, and then you have a layer of carbon nanotubes, another metal layer, sort of a sandwich fashion. That's not random, and see how that would impact the conductivity and mechanical strength. So there are many different structures then now we can explore, and then we can compare that with the experimental outcome. And so that's the direction that I am taking right now.
I'm not sure if there's an easy way for you to answer this, but it seems that on that nanoscale, materials are going to behave very differently, even though, you know, they might have the same kinds of structures, or they may appear to have the same kinds of structures as things on a macroscopic scale. Can you talk about how the models, because, you know, I imagine that it's not a mathematical model that's the same as measuring